Oh, welcome to West Virginia. I think I did that wrong. Anyways, welcome to West Virginia. I brought Ellie here with me because she's gonna. She's gonna deliver joke of the day because she's the creator of the joke book, and it's the best part of the day. Take it away, Ellie.
Yeah, it is. All right. So a group of chess enthusiasts checked into a hotel and were standing in the lobby discussing their recent tournament victories. After about an hour, the manager came out of the office and asked them to disperse. But why? They asked. He said, because I can't stand chestnuts boasting in an open foyer.
Oh,
I should leave.
But let's open. Thank you, Ellie. Let's open ourselves up, though, to rational equations with variables in the denominator. So we've looked at rational expressions before, and we discovered that whenever you have rational expressions, because rational means not rational, dude, but means can be written as a fraction, then that means that our rational expressions are basically just fractions. And so if you're adding and subtracting your rational expressions, then that means that you need to get a common denominator, because common denominator is what it takes to get or to add or subtract rational expressions. In other words, to add or subtract fractions. So here's the idea. These are rational equations, so that means that these are equations that have fractions in them. Now, we've dealt with equations that have fractions with them before, and we found out that there were two methods for dealing with it. So that's what's going to happen here again. The only difference between what we talked about before and what we're talking about now is that now the equations are going to have variables in the denominator. We've never dealt with this before. But you're going to find out that you still are going to have two methods for solving these equations. Now recall, method one, this should sound familiar, because method one says, okay, we have fractions, and we're going to either add or subtract those fractions. Let's flip this around and show you the first example that we're going to be dealing with so you can understand what I'm talking about. So here's the first example of our rational equation. Again, fraction here, fraction here, fraction here. Now they don't all have to be fractions, but you at least have some fractions in there. And the biggest thing to note is you've got a variable in the denominator here and a variable in the denominator here. So that first method says, okay, I'm subtracting these two fractions. And we have to recall what it takes to subtract fractions. This is where we say, all right, in order to subtract fractions, what has to happen is you have to get that common denominator. So you're going to take a look at all the denominators are there. You're going to get that LCD, that least common denominator. And then what you're going to do is you're going to say, okay, well then, once I get that common denominator, recall that when you had basic fractions, let me go ahead and get through this first example. I'm going to flip this board over and over and over again, but I think this will make a whole lot more sense if I walk through the first example. So I'm going to look at this rational equation. I'm going to say, okay, since I'm subtracting these equations, I have to get a common denominator all the way across. So I'm going to look at the 3z, the 5, and the 15z, and I'm going to say, what is the smallest denominator they would all go into? Well, the 3, the 5, and the 15 will all go into a 15. So I'm going to convert everything into denominators of 15. But then notice this one has a z and this one also has a z. So I'm going to make sure that every single denominator has a z in it. So now what I'm going to do, recall that whenever we got common denominators, we had to adjust those numerators. So what I'm going to do next is I'm going to say, well, what would it take to turn this 3z into a 15z? I would simply multiply it by a 5. And recall that I don't want to change the value of this fraction, only what it looks like. So if I multiply the denominator by 5, I also need to multiply my numerator by 5 as well. Because again, in order to change just its looks, but not its value, 5 over 5 is a 1, and whenever you multiply by 1, you do not change value at all. So I'm not going to change the value of this fraction by taking this 2 and also multiplying it by 5 and getting a 10. So 10 over 15z has the same value as 2 over 3z. And I'm going to do the same thing for every one of these fractions. So I'm going to take this 5 and I'm going to multiply it by a 3 to create a 15, but it also needs a z. So I'm going to multiply this fraction here by a 3z in order to get that common denominator. So 3z times 5 will give me 15z, and like we discussed over here, what I do on a denominator, I have to do on a numerator so that I don't change value. So I'm going to multiply my numerator by 3z as well. 3z times 1 is a 3z. And I am subtracting these two fractions, so I need to put my subtraction symbol in there. Now this one, 15z, it's already there, so I don't have to adjust anything. So that's what this second step meant in this first method. We said get that least common denominator. We did that. We said multiply those numerators and denominators by factors that will create that LCD. So I multiplied the denominator by 5. I multiplied the numerator by 5 as well. I multiplied the denominator by 3z. I multiplied the numerator by 3z as well. Now once we do that, let's flip back over here. Recall that whenever you have basic fractions and you get that common denominator and you adjust all those numerators, then what you do is you go ahead and combine the numerators. So what's going to happen here is I'm going to say I'm going to keep that denominator because I like those common denominators. I worked really hard to get it, so I'm going to keep it. And I'm just going to combine those numerators. And I'm going to say 10 minus 3z, which I can't really do. So I'm just going to let them sit beside each other like this, 10 minus 3z, and that will equal my 16 over 15z on the other side. Now at this point what happens is I say, okay, I've got two equivalent fractions here, and if the fractions are equivalent, that's what this equal sign means. So think of the equal sign, think of your equation as a pan balance. We've talked about pan balance before. And so what happens here is if the pans are equal and that fulcrum in the middle says these two sides are balanced out, then what happens is this fraction is in this pan right here. And this fraction is in this pan right here. So it's all balanced out. If the denominators are the same and these fractions are equivalent, then what has got to be true about those numerators? Absolutely. For this fraction to have the same value as that fraction, then that means that this numerator of 10 minus 3z had better be the same as that numerator of 16. So in other words, that 10 minus 3z had better be a 16. If this side over here, this numerator, is anything other than a 16, it's not going to be balanced out. It's going to be tipped out of whack. And it is balanced out. So the 10 minus 3z had better be a 16. So flipping back to those steps then, once we multiplied those numerators and denominators and adjusted all of our fractions, we could add or subtract the fractions. We'll get back to this here in just a minute. And then we said, okay, we have equivalent fractions. When you have those equivalent fractions, that means those numerators have got to be equal because those denominators are equal. So basically at that point, you can just drop the denominators. Just drop them because the numerators have got to be the same. And you saw that we had an equation that was fairly easy to solve. So we can go ahead and solve that resulting equation, and in this case we're going to solve for z. And so in order to solve this equation for z, what I'm going to do is I'm going to subtract that 10 from both sides. That will give me negative 3z equal to 6. And then you know you need to divide by negative 3 on both sides. And so that'll give me z equal to a negative 2. So that's my solution to that equation. I just need to be very careful about restrictions on the domain. And we've talked about restrictions on the domain before. And remember, what that means is I've got to ensure that whatever I plug in here and here does not create a 0 in the denominator of the fraction. Because remember, if there's a 0 in the denominator of the fraction doesn't exist anymore. It's undefined. So I need to make sure that this 3z, my restriction on the domain, the RID, oh my goodness, not a RID, a restriction on the domain, the rod, I need to make sure that this 3z here, it had better not be a 0. And in order for that to happen, if I divide both sides by 3, my z is not going to be a 0. And then here, 15z, I need to ensure that it is not a 0. And so yet again, if I divide both sides by 15, I'm going to get one more time, 0 divided by 15, yet again is z not equal to 0. So that is my only restriction on that domain. Any other number will be fine. Any other number will work. Negative, positive, fraction, decimal, irrational number, everything, just not a 0. But recall what I came up for with my solution, what I concluded to be my solution, was a negative 2. That is not a part of the restriction on the domain. So when I put a negative 2 in here and here, not only will it create this left side to be the same as this right side, it also will not cause a 0 in the denominator here, nor a 0 in the denominator here. So this z being a -2 is perfectly fine. It is not a part of the restriction on the domain. So that's how method 1 works. Let's flip that back over one more time and recall those steps. Get that LCD, get that least common denominator, multiply your numerators and your denominators by factors that will create that LCD. So adjust every fraction so that they're equivalent. Multiply denominator and numerator by the same thing, denominator and numerator by the same thing, denominator and numerator by the same thing, all the way across. And then, once you've got that common denominator, you can go ahead and add or subtract your fractions. Now, here again, we'll come back to this. If you're subtracting, typically you're going to distribute that negative all the way through the second parentheses. But see, we didn't have that situation right here. We just said 10 minus 3z. We were perfectly fine. But now remember, once we've done that, we will have two equivalent fractions on either side of the pan balance. And if this fraction has the same value as this fraction and their denominators are the same, then that means those numerators have got to be the same. That is the only way for the fractions to be equivalent. So because of that, we can drop that denominator. Gives us an equation that's pretty easy to solve. We can solve it, but we better check that solution with the restriction on the domain, because if it is the restriction on the domain, then that solution is what we call an extraneous solution. Now, that's the first method. There is a second method for solving these rational equations. The second method says, you know what? Because I know how to multiply those fractions, that I'm going to cancel on the diagonals, I'm going to cancel up and down, and then I'm going to shoot straight across. Because I know that, I can multiply every single term by that LCD. Literally every single term. And what will happen, the beauty is, this will get rid of all the fractions in the very first step. You will end up in one step with an equation that's pretty easy to solve. And then you're just going to check that restriction on the domain like we did here. So let's take a look at that second method in this very same example. So what happened here is we started with our 2 over 3z minus 1/5 equal to 16 over 15z. And I'm going to take that equation, I'm going to multiply every single term by that LCD. Now recall the LCD is still 15z. So in my very first step, I'm going to take the whole thing, let me just write it down here. I'm going to take every single term, the whole thing, do it this way, take the whole thing and multiply it by that 15z. But that means every single term will get multiplied by the 15z. So the first term will get multiplied by 15z, the second term will get multiplied by 15z, and finally in the back, my 16 over 15z will also get multiplied by 15z. Now recall, like I said, when you multiply those fractions, you're going to cancel on the diagonals. So here's where the beauty unfolds. This is the amazing, gorgeous thing about this method. When I go to multiply right here, and again, I'm going to cancel on those diagonals. If I put that 15z over a 1, when I check this diagonal right here, the z's will completely cancel out. In addition, 3 goes into 15 5 times. So I'm simply left with 2 times 5, which is 10. Poof! Fractions are gone. It's amazing. Here, I'm going to do the very same thing. I'm going to put my 15z over a 1, and then I'm going to cancel on that diagonal right there, and then I'm going to say, oh, okay, 5 goes into 5 once, 5 goes into 15 3 times. I'm left with 1 times 3z, which is just a 3z. So I'm subtracting that 3z. And then right over here, again, cancel on those diagonals. 15z will cancel out with 15z. I'm just left with a 16. Notice that this equation looks exactly like this one right here. Same thing. So in one step, I got rid of all the fractions and I'm ready to go. So I'll subtract that 10, I'll divide by that -3, I'll get the very same answer of -2. I will still check with the restriction on the domain, and the restriction on the domain is still going to be a 0 because this is what I started with, this equation, and that -2 still is not a part of the restriction on the domain, so that -2 is going to be perfectly fine. So the second method is beautiful because it gets rid of those fractions in one step. We just have to be very careful about that second method, because the second method you cannot do when there is no equal sign. Because when this equal sign is gone and this is all you have, when you multiply this term by a 15z, you change the value of that fraction. And you don't really want to change the value of it at all. You want to retain the value. So when that equal sign is not there and you simply have a rational expression, because remember, expression does not have an equal sign. When you put an equal sign in an expression, it turns into an equation. But when the equal sign is there, this second method is totally legal, totally fine, because basically what you're doing, when you multiply every single term by that 15z, you're multiplying this side of the equation by 15z, and you're multiplying this side of the equation by 15z. So basically what's happening there is you're taking your pan balance, you're multiplying this pan by 15z, and you're multiplying this pan by 15z. So you're doing the same thing on both sides of the pan balance, and that's what's making it legal. You're not tipping it out of whack. So like I said, second method, gorgeous. I use the second method all the time. I love the second method. But I know that when the equal sign's not there, I cannot do this because I'm changing the value of that fraction into a 10, and I'm changing the value of this fraction into a 3z. And you know that this fraction does not have the same value as a 10. You know that fraction does not have the same value of the 3z. Now when I did this and I multiplied the numerator and the denominator by 5, that's okay. And I can do that method, method 1, even when there's not an equal sign. Because when I multiply by 5 over 5, I'm multiplying by a 1. I'm not changing the value of that fraction at all. Same thing here. When I multiply by a 3z over 3z, I'm not changing the value. 3z over 15z simplifies to 1/5. 10 over 15z simplifies to 2 over 3z. This fraction have the same value. This fraction have the same value. So my point is simply this. If you are one who will get confused that I'm allowed to do method 2 when there's an equal sign, I'm not allowed to do method 2 when there's no equal sign, then for you, this second method doesn't exist at all. Because the first method of adjusting all these LCDs, multiplying numerators and denominators by the same factor, that method will work whether you have an equal sign or whether you don't have an equal sign. Method 1 works all the time. So method 1 is for those who will get confused. But if you're one who won't get confused and you know that this second method is only allowed when there's an equal sign, it's a fantastic method to use. So let's try a few more examples just to make sure that we're very comfortable and solid with this. Let me get this example out of here. I don't really want to erase these steps right yet. I want to be able to refer to those one more time, and then I'll erase them and really take off with these. So let's take another example, example B, and this one is going to say, pardon me very much, going to say 2x minus 2 over 3x equal to 4x minus 6 over 5x. So once again, we're going to deal with method 1 and method 2. Method 1 says, okay, let's retain the idea that we have fractions in here. Let's get that LCD. So I'm going to look at my 3 and my 5, and I'm going to say yet again, 15 is the smallest number they will both go into. And I'm going to look at the fact that they both have x's. So 15x is my LCD. So I'm going to look at this denominator. I'm going to say, what would it take to turn a 3x into a 15x? I need to multiply by 5. So I'm going to multiply my numerator by 5. I have to be careful though. I'm multiplying the entire numerator by 5. All of it. So me, I'm going to put a parentheses around there just to remind myself all of it gets multiplied by 5. So 5 times 2x is 10x, and 5 times negative 2 is a negative 10. Now I'm going to look at this one. I'm going to say this 5x needs to be multiplied by a 3 to turn it into a 15x. So I'm going to multiply yet again the entire numerator by 3. And 3 times 4x is 12x. 3 times negative 6 is negative 18. So now I have these equivalent fractions. So yet again, that pan balance idea that this is the fraction that's in this pan, this is the fraction that's in this pan, it's balanced out, and if it's balanced and they're equal and the denominators are the same, that means those numerators have got to be the same. So we can drop that denominator and we can just focus on these numerators right here. And so what that leaves me with is an equation that's pretty easy to solve. 10x minus 10 equal to 12x minus 18. And I can run with that. So I'm going to subtract a 10x on both sides. And that will give me, be very careful, negative 10 equal to 2x minus 18. Sign in front's a sign that goes. You put that name tag on the front when you go to that meeting. You don't put your name tag on the back because then I can't tell you who you are. But that sign in front's a sign that goes. You take the name tag off once you leave the meeting, but not until you leave. So now I've put all my variables on this side. Constants will go on the other side. I'm going to add an 18 and I'm going to add an 18. So negative 10 plus 18 is 8. And at this point, I'm just simply going to divide by 2 on both sides. That means that my x is a 4. But once again, be very careful. Check that restriction on the domain because the answer that I got, I don't want it to be something that will cause a 0 in the denominator. So in this denominator, that 3x, it had better not be a 0. And when I divide by 3 on both sides, that x had better not be a 0. And then on this one, the 5x had better not be a 0. And when I divide by 5, that means my x had better not be a 0. I'm getting the exact same restriction on the domain in both cases. But the beauty is, I didn't say x should be a 0. I said x should be a 4. 4 is not a part of the restriction on the domain, so my 4 is perfectly fine. So that, again, is method 1. Look one last time to take a look at those steps. We got that common denominator. We adjusted the numerators and the denominators. We didn't have to add or subtract anything, but because those fractions were equivalent, and that meant those numerators have got to be the same since the denominators were the same, and so we dropped our denominators and we solved the resulting equation. We checked that restriction on the domain. Now, let's take a look at that second method. Second method, recall, said let's take this equation and instead let's use the LCD, but we're going to use it in a different way. We're going to take this equation and we're going to multiply every single term by that LCD. So I'm going to take both sides and I'm going to multiply them by that 15x. So what happens here is, and I'm going to just, actually I'm not going to erase anything because in one step I'm going to end up at the same spot. When I multiply this by 15x, notice what happens here is that 3x, the x's cancel, 3 goes into 15 5 times. So I'm going to say 3 goes into 15 5 times, the x's cancel out completely. I've got 5 times this entire numerator. 5 times 2x minus 2. And then on this side, when I multiply it by 15x, again the x's cancel. 5 goes into 15 3 times. And so on this side, I'm going to have my 4x minus 6 times 3. And then this round equation is pretty easy to solve. I know I'm going to distribute that 5 through, and when I do, 5 times 2x is 10x. 5 times negative 2 is negative 10. And when I distribute here, 3 times 4x is 12x, and 3 times negative 6 is a negative 18. So I'm at the very same spot that I was before. And we know that that means subtract a 10x here, subtract a 10x here, and then just run on down with it like we did before. And once again, we're going to check that restriction on the domain. I know that x better not be a 0. I didn't come up with that. My x is going to be a 4. So putting a 4 in here, 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 and here will make this side and this side equal to each other, and I will not have zeros in the denominators, so the fractions will still exist. So there's that second method one more time. We multiplied absolutely everything by the LCD, came up with an equation that was very easy to solve, and we checked our restriction on the domain. Okay, just a few more examples because I want us to be very good at it, and I don't want anything at all to shock us. So let's go back. I'm going to create myself a little bit more space here to work with. Enjoy the scenery behind me, the lovely, lovely West Virginia. So, my next example, where did I leave off? Okay, it's letter C. We are going to have a 2 over x minus 2 equal to an x over x minus 2 minus a 2. Whoa, things are going crazy now because before we just had one variable in that denominator. It wasn't a big deal. It was just maybe a 3x. Here we've got some subtraction going on. But remember that in method 1, we said in method 1 what we wanted to do was we wanted to get common denominators all the way across. So I'm going to put my 2 over a 1, and I'm going to look at every one of these denominators, and I'm going to say, you know what? If this denominator was an x minus 2, they would be the same everywhere. So what I'm going to do is I'm going to multiply this one by an x minus 2, and what I do on a denominator, I have got to do on up on a numerator. I'm going to take that 2 and multiply it by x minus 2. So this one's already good to go. This one's already good to go. But this one, what I'm going to do is I'm going to multiply that 2 by the x minus 2 and get a 2x minus 4 over the x minus 2. So I have got that common denominator all the way across. I have adjusted those numerators. Now that I've got common denominators, I'm going to go ahead and combine those numerators. Here's where I said we have to be very careful, because recall, I'm subtracting the entire numerator, all of it. So I'm going to put a parentheses around it to remind me I am not just subtracting that 2x, I'm also subtracting the negative 4. So that means that I need to take this negative right here, I need to distribute it all the way through that parentheses. That was that step that I said, we'll get to this in just a minute. We're there now. So when we distribute this negative all the way through that second parentheses, we're going to get a negative 2x plus 4 over the x minus 2. And then we've got a 2 over x minus 2 equal to an x over x minus 2. And what happens is it turns it into an addition problem. Now that I have common denominators all the way across, I can go ahead and combine up those numerators. So once I combine up those numerators, and I'm allowed to do that because I've got common denominators here. And when you add up fractions, once you've got that common denominator, you can combine the numerators. So an x plus a negative 2x is a negative x plus that 4, because that 4 doesn't combine with anything. And I'm combining those up. I'm going to keep that denominator. Remember, I worked awfully hard to get it, so I'm going to keep it. And on this side, I have a 2 over x minus 2. So here we are at that point where in this pan is that fraction, in this pan is this fraction, and it's all balanced out. And if it's balanced out and the denominators are the same, the numerators have got to be the same. So therefore, that means that this 2 has got to be that numerator of negative x plus 4. So my 2 is going to be a negative x plus 4. We are down to an equation that's pretty easy to solve. So what I'm going to do is I'm going to subtract that 4 from both sides. 2 minus 4 is a negative 2. And now I'm going to divide both sides by a negative 1. And remember, just dividing by a negative on both sides simply changes every single sign. So I end up with a 2 equal to x. Now, check the restriction on the domain, but let me step back a second before we check the restriction on the domain. A lot of people get very confused from here to here. So one thing that I want to point out is, notice that eventually, right down here, we are going to drop those denominators because we've got common denominators all the way across. So a shortcut that you can take is right here. As soon as you get those common denominators and as soon as you adjust that numerator right here, you can go ahead and drop those denominators right immediately. And if you go ahead and drop your denominators right here, you will end up with 2 equal to x minus 2x minus 4. And then what you'll do is you'll distribute that negative all the way through that parentheses, and when you do, you'll get 2 equals x minus 2x plus 4. And some people find that to be easier to deal with, because right here a lot of people get confused about distributing that negative through the numerator but not the denominator, and that really, a lot of people struggle with that. So like I said, you are allowed to drop this denominator as soon as you get the common denominator all the way across. Well, as soon as you adjust this numerator right here, you can go ahead and drop that denominator. And then here when I combine the x minus 2x, that sends me right down here. So that is a step that you can take. But remember, I need to check that restriction on the domain, the rod, and I go back to the beginning and I say, okay, my denominators here were both the same, so I only need to check it once. That x minus 2 had better not be a 0. What would make it a 0 would be if that x was a 2. I don't want that to happen. And I say, whoa, wait a minute. That's what I said my answer was. So in other words, this 2 is the only number that I can put here, here, and here, and get this right side to be the same as this left side. This is the only number that'll work. The only number that'll make the left side and the right side be the same value. But the only number that will work when I put it in here causes 0 in that denominator, this one as well, but causes a 0 in the denominator, and suddenly, poof, that fraction doesn't exist anymore. Poof, that fraction doesn't exist anymore. That's not okay. I cannot have undefined fractions. So the only number that will work won't work. So therefore, what's my solution? You're exactly right. That befuddled look that I can see on your face, you're going, you're exactly right. That means I don't have any solutions at all. So my answer then is going to be no solution, because the only thing that should work won't work. Now, let's take a look at that second method. Recall the second method said, and let me just go ahead and write over top of this stuff. I won't be writing much because this second method is beautiful, because remember, the second method gets rid of those fractions right in that first step. It says, let's take this and let's multiply the LCD. Take absolutely everything and multiply it by that least common denominator, which we already figured out was an x minus 2. So what happens here is when I take that x minus 2 and I multiply it here, it's going to cancel with this, and I am just left with a 2. And when I take that x minus 2 and I multiply it here, it's going to cancel this one. I am just left, multiply it here, cancels out, I'm left with a 2. Multiply it here, cancels out, and I'm left with an x. When I multiply it here, I've got a negative 2. Actually, let me step it in right here. I'm not doing a good job of explaining this. Let me step back a second. Clean this up. All right. So when I take this first term, 2 times x minus 2, and multiply it by the x minus 2, they're going to cancel, and I'm just left with a 2. When I take my x over x minus 2 and multiply it by the x minus 2, these will cancel, and I'm just left with an x. But when I multiply here in the back, nothing will cancel at all, and I'm left with a minus 2 times x minus 2. This is an equation that's pretty easy to solve, because what I'm going to do at this point is I'm going to distribute that negative 2 through. When I distribute a negative 2 through here, I get a negative 2x. When I distribute the negative 2 here, I get a positive 4. And now I've got this equation. And when I take an x minus a 2x, I get a negative x, and I run with it just like I did before. So yet again, you can see that either method is perfectly fine. You can retain those fractions, get that LCD all the way across, adjust your numerators, combine up those fractions, and drop that new denominator, or you can go ahead and get rid of it in the first step and multiply everything by the LCD. But notice that we did have a problem because of the restriction on the domain. You need to check that. This is what we call an extraneous solution. Extraneous solutions are ones that should work, but they don't because they cause zeros in denominators. Also called an extraneous root. Either answer or either terminology will be perfectly fine. They all mean no solution. Okay, so let's try another one. Like I said, I really, lots of people struggle with these. So I like to have a lot of examples so that we feel very comfortable and nothing shocks us. We've seen everything that could possibly come across our way. Once again, enjoy this lovely scenery. Enjoy a baguette while I clean this board up. And we are now on example D. And we're going to do a 3 over an x plus 4 minus 7 equal to a negative 4 over x plus 4. So once again, that first method says, hey, let's keep these fractions in here. Let's get those common denominators all the way across. And so I put my 7 over 1, I look all the way across, and I go, hey, if they were all an x plus 4, I'd have something beautiful. So my LCD is going to be an x plus 4. The first one's there. I'm going to multiply this by an x plus 4, which means I also multiply my numerator by an x plus 4. So I get negative 7 times x plus 4 over x plus 4. And then this one's already there, so I'm going to leave it alone. And like I discussed before, I'm going to distribute that 7 through. I'm going to distribute the negative through as well. And when I do that, I'll get a negative 7x minus 28 over my x plus 4, turns it into an addition problem. Or if you would prefer, as soon as you get here, you could go ahead and drop all those denominators. Because what's going to happen is when you drop all the denominators and you end up with 3 minus 7 times x plus 4 equal to a negative 4, that's where I'm going to end up with this. Because at this point, I've got common denominators all the way across. I've adjusted all my numerators. I'm going to combine those numerators. And I'm going to say 3 plus negative 28 is going to be a negative 25. And then plus that negative 7x equal to a negative 4. And I've dropped all those denominators because I've combined them all up. In other words, when I combine these two, it's all over an x plus 4. And this is over an x plus 4. But I can most definitely drop them now because this fraction here is equivalent to this fraction. And when the fractions are equivalent and the denominators are the same, we can drop them and just keep that numerator. That negative 25 minus 7x had better be a negative 4 because if this is anything other than a negative 4, the two fractions are not going to be the same. Now notice when I dropped it right here and I landed on this one that's written in black, if I distribute this negative 7 through, I will get negative 7x minus 28, which is right here, and that 3 minus 28 will land me right back down here at the negative 25 minus 7x. So I'm getting in the same place regardless of the route that I take to get there. Because like I said, this ends up as a 3 minus 7x minus 28 equal to a negative 4, and 3 minus 28 is right down here at negative 25. Now, I can solve this equation by simply adding 25 to both sides. And that gives me negative 7x equal to 21. And I know that I'm going to go through and divide both sides by negative 7. I'm running out of room, so I'm going to slide that over here. Negative 7x equal to 21. I'm going to divide by negative 7. And that gives me x equal to negative 3. But don't forget, check that restriction on the domain. I've got to be careful that the solution I came up with, it better not cause a 0 in the denominator. Same denominator here and here. So I only need to check it once that x plus 4 had better not be a 0. And if I subtract 4, that means the x had better not be a negative 4. That's my restriction on the domain. But that's not what I said x should be. I said x should be a negative 3. So my answer is perfectly fine. Now, let's check method 2 one more time. So method 2, recall, it says, let's get rid of those fractions in one step. Let's take every single term that I see here and multiply absolutely everything by that LCD of x plus 4. And so like we said, when we multiply this by x plus 4, that's going to cancel out completely. I'm left with a negative 4. When I multiply this by x plus 4, I get this right here. And when I multiply this by x plus 4, they cancel out, and I'm left with a 3. And so yet again, when I distribute that through, I get this equal to my negative 4. And 3 minus 28 is a negative 25, lands me right here. I add that 25 and keep on going. And yet again, check it with a restriction on the domain. Beautiful that we've got two methods to choose from, and you don't have to use both methods. You don't even have to know both methods. You pick the method that you like and you run with it. Just remember that when the equal sign is not there, this second method does not work at all. You are stuck with that first method if the equal sign is not there. Okay, so hopefully we feel comfortable with it. Hopefully we've settled in with it. But I want to show you some situations where that denominator is not as pretty as these are. Now you may be saying, now wait a minute, that denominator wasn't so pretty. It was an x minus 2. But notice it wasn't that bad because pretty much it was the same denominator all the way across. But sometimes the denominators will look crazy. And when they're crazy, what on earth are we going to do to find that common denominator? Well, sometimes you have to factor to get that LCD. So sometimes I believe I'm on 3, or nope, I'm on 4. Roman numeral 4. Sometimes you must factor to get the LCD. And I've got 2 examples of this. And we're going to solve each one of these. So in my first example, I'm going to have a 2 over an m plus 4. And we're going to add to that a 5 over an m squared minus 16. And that will equal a 1 over m plus 4. Whoa, those denominators are crazy. Whoops, this should actually be an m minus 4. There we go. Crazy denominators. Now recall, method 1 said, let's get those LCDs, let's retain the fractions, and let's get LCDs all the way across. But the problem is, as they are written, I really can't quite tell what the LCDs are. But if I take this one and I factor it, I'm going to be able to look at each of those denominators and figure out what needs to happen to make them all look the same. This one will factor as an m plus 4 and an m minus 4. Nothing common that I can divide out of every term. Back sign here tells me I want opposite signs. I'm going to split this up as an m and an m. I'm going to split this up as a 4 and a 4. And when I check the outsides, negative 4m and the insides, positive 4m, yeah, they'll cancel. And I needed them to cancel because I don't have a middle term. So this is how this one factors. So now when it comes to needing to find that LCD, I'm going to look at each one of the denominators and I'm going to say, now wait a minute. If this one had an m minus 4, it would look just like this one. And if this one had an m plus 4, it would look just like all of them. So that's my LCD, m minus 4, m plus 4, m minus 4, m plus 4, m minus 4, m plus 4. So like we said before, I don't want to change the value of this fraction, only what it looks like. So I'm going to take my numerator and multiply it as well by an m minus 4. This one doesn't need multiplied at all because it's already there. And I'm going to take this one and multiply it also by an m plus 4. So now that I've got those common denominators all the way across, I'm going to adjust those numerators. 2 times m minus 4 is a 2m minus 8 over, and I'm going to get a little lazy now. I'm never lazy, but this is the one time I'm going to get lazy. Common denominator. Just put a squiggle mark because I'm going to get tired of writing out all those common denominators. 5 over common denominator equal to m plus 4 over common denominator. Now recall us talking about that we are going to combine these two numerators and keep the denominator. So 2m minus 8 plus 5, well negative 8 plus 5 is a negative 3. So I have a 2m minus 3 over common denominator equal to an m plus 4 over common denominator. But recall, now we have this fraction equal to this fraction, and if the fractions are the same, or have the same value, and the denominators are the same, then the numerators have got to be the same. So in other words, I can ignore these denominators and I can just drop them. So I could have dropped them right up there. And if I dropped them right up there, then I would have had, and let's insert that in here, I would have had a 2m minus 8 plus 5 equal to an m plus 4. And sure enough, a negative 8 plus 5 will be a negative 3. And this is what I had over common denominator, and most definitely at this point I can drop those denominators without a doubt. So like we said before, once you've got the common denominator all the way across and you've adjusted your numerators, you can go ahead and drop them right there. So now I'm going to solve this equation. I'm going to subtract an m from both sides, giving me m minus 3 equal to 4. I'm going to add that 3 here and add that 3 here, and that will give me m equal to 7. I need to check that restriction on the domain because I want to make sure that 7 is not going to cause problems. But notice that my denominators are not the same. So I need to check this denominator of m plus 4. I don't want that to be a 0. which means my m had better not be a negative 4. This one, my m minus 4, I don't want that to be a 0, so my m had better not be a positive 4. And on this one, I need to check its factored form. Factored form right here. So that m plus 4 had better not be a 0. We already took care of that. The m minus 4 had better not be a 0. I already took care of that. So here's the two restrictions on the domain. M had better not be a negative 4. M had better not be a positive 4. Well, I didn't say either one of those. I said m is going to be a 7. So my answer is perfectly fine. Now, let's take a look at that second method. The second method, remember, it said that I'm going to take this equation, I'm going to multiply everything by that LCD. Literally every single term will get multiplied by the LCD. So let's get this out of here so that I can show you how that one works. Enjoy the scenery! Enjoy the scenery! Okay. So remember, I'm going to take this equation in method 2 and I'm going to multiply every single term by that LCD. So we've already figured out the LCD is m plus 4, m minus 4 because we factored this. So I'm going to take every single term, multiply by an m plus 4, m minus 4. Every single term. So when I take my 2 over m minus 4, or sorry, m plus 4, and multiply it by my LCD, notice the m plus 4's cancel out. And I am just left with a 2 times m minus 4. When I take this one, and I multiply it by my m plus 4, m minus 4, notice what happens is it cancels this out completely because this factored as an m plus 4, m minus 4. So it cancels out completely. I am just left with a 5. Let me change the colors here because I think this is starting to roll into each other. So here I'm left with a 2 times m minus 4, and here I'm left with a 5. And then back here, when I multiply this one by an m minus 4, m plus 4, this is really getting out of hand. I am so running out of room. All right, multiply this one by my m minus 4, m plus 4. Notice what's going to happen is the m minus 4's will cancel. And I will simply be left with an m plus 4. So I'm left with the line in the black once I multiply everything by the LCD. M plus 4's will cancel. I'll be left with 2 times m minus 4. This will cancel completely. I'll be left with a 5. And the m minus 4's will cancel. I'll be left with an m plus 4. Now in this black equation, I will distribute my 2 through. 2 times m is 2m. 2 times negative 4 is negative 8. Plus 5. Voila, there we are. And we've got an equation that we can solve. We combine these two like terms and then we run with it and get the same exact solution. So you can see that even though sometimes you have crazy denominators, you still have both methods to choose from. You can retain those fractions and get the common denominators all the way across, adjust those numerators, combine it and drop the denominators, that is, drop the denominators, or you can multiply everything by that LCD and get rid of those denominators in the first step. Still need to check that restriction on the domain to make sure everything that you say is going to work really will work. The only difference here is finding that LCD sometimes is a little more complicated. You might have to factor to get your LCD. So let's try one more example and then I think that'll do it for us with these rational equations that have variables in the denominator. One last example, and it's going to be very similar to the one that we just looked at because that was a bit of a challenge. Alright, so we are on example B, and my equation is going to be 6 over x plus 3 minus 5 over x minus 2 equal to negative 20 over x squared plus x minus 6. So once again, method 1 says, let's keep those denominators all the way across. Let's get that LCD. So I'm going to have to do a little bit of factoring to figure out what that LCD is. I'm going to take this one and factor it. Now notice there's nothing common that I can divide out of every single term. So I'm headed for that double parentheses. Back sign tells me signs are different. One's a plus, one's a minus. Split this into the front slots, x and x. Split this into the back slots, so I want two numbers that are going to multiply for 6. They're going to subtract for a 1 because these signs are different. That will be a 3 and a 2. So I'll put my 3 here and 2 here. Check my outsides and insides to make sure it works. Out here I get a -2, in here a +3. Yep, that gives me the positive x that I wanted. So this is my factored form. So now that I look at all these denominators, I say, no, wait a minute. If this one had an x -2, it would look just like that. And if this one had an x +3, it would look just like that. So therefore, I'm going to take this numerator and multiply it by an x -2. I'm going to take this numerator and multiply it by an x +3 yet again because I don't want to change the value of the fraction, only what it looks like. So here, this becomes 6x - 12 over common denominator. This becomes 5x + 15 over common denominator. And this becomes -20 over common denominator. And we said before, now that the denominators are all the same and all these numerators have been adjusted, I can drop the denominators. I have to be very, very careful though, because I am subtracting this entire numerator right here. Not just that 5x, the whole thing. So I'm subtracting all of that. But now I'm down to an equation that's pretty easy to solve. So I'm going to distribute that negative through and get a 6x - 12 minus 5x minus 15 equal to -20. And now I'm going to combine up those like terms. 6x minus 5x is x. -12 minus 15 is a -27. And I can solve that equation. I'm simply going to add a 27 to both sides, giving me x equals 7. So now I need to check that restriction on the domain to make sure that's okay. And so what that means is that x +3, it had better not be a 0. If that's the case, x better not be a -3. And then here, that x -2, it had better not be a 0, in which case x had better not be a 2. And this third one, on its factored form, well, that x +3, I've already checked it. The x -2, I've already checked it. So here's the two numbers that x cannot be. I didn't say x was going to be either one of those. I said x was going to be a 7. So my 7's perfectly fine. So that's method 1. Let's take one more glance at method 2. And recall, method 2 says I'm going to get rid of those fractions in the very first step. So method 2 says, let's take that LCD that we found, that x +3, x -2, and let's multiply every single term by that LCD. So in method 2, I'm going to take, hold on a second here, method 2, I'm going to take my 6 over x +3, I'm going to multiply it by the LCD of x +3, x -2. And notice that the x +3s are going to cancel. I will be left with 6 times x -2. And then I'm going to take this second term and I'm going to multiply it by the LCD of x +3, x -2. And the x -2s will cancel. And I'm left with a -5 times x +3. And then here in the back, I'm going to multiply this one by that LCD of x +3, x -2. But remember, it's going to cancel that whole denominator. I'm left with a -20. So now I'm down to an equation that's pretty easy to solve. I need to distribute my 6 through, and when I do, 6 times x is 6x, 6 times -2 is -12, -5 times x is -5x, and -5 times 3 is a -15. There it is, and I'm going to run with it and do the exact same thing. So, Hopefully you're seeing that regardless of whether you've got fractions where the denominators need to be factored a bit to find the LCD, or the simple cases that we started with where we don't need to do any factoring, the LCD is kind of right in front of us, just do a simple multiplication or even not a multiplication at all. Comes down to this. Method 1, retain those fractions, adjust those numerators by multiplying by factors that will create the LCD. Once you've got the fractions adjusted, you can drop the denominator and combine up all those numerators. Being very careful, you may have to distribute that negative all the way through that second parentheses if you're subtracting. But you come up with an equation that's fairly easy to solve. Check that restriction on the domain to see if your answer will cause a problem. If it does, it's an extraneous solution. You have no solution. Method 2 says, okay, use that LCD, but multiply everything by the LCD so that in one step you have gotten rid of all the fractions. You are down to an equation that's very easy to solve. Remembering you have to take that negative and distribute it through. I hope it helps. Have a great day.